let's now do the reverse with another integral, of course, though. We can't just reverse what we just did. So I'd like to rewrite the integral from negative 2 to 2, integral from 2 minus root 4 minus x squared all the way up to 2 plus root 4 minus x squared, integral negative root 4 minus x squared minus y squared all the way up to positive root 4 minus x squared minus y squared, of the function x squared plus y squared quantity to the third power times cosine of z dz dy dx in cylindrical coordinates. Okay, now this is going to be rather challenging, but if we look at this first part here, once the bounds for z would be figured out, this projection here, we're noticing, okay, the outside integral is the x, and we see that in the projection that x goes between negative 2 and positive 2, while y goes between, we read it just directly off of the middle integral, y goes from, at the smallest, 2 minus root 4 minus x squared all the way up to 2 plus root 4 minus x squared. So let's draw a picture of what that projection really looks like, right? So the thing to note really is if you look at x squared, let's see, so let's take a look at what 2 minus root 4 minus x squared just equals y is. And so to make this look a little more, what should we say, like more like something that we might recognize, maybe we should first add the radical to both sides. How about that? Let's do this. How about we'll do let's deal with this positive side first. I think that'll actually be easier to work with here. So y equals 2 plus root 4 minus x squared. Well, if we subtract 2 on both sides, y minus 2 is equal to root 4 minus x squared, then we can actually square both sides, and let's not work too hard on the left side. So how about y minus 2 quantity squared is equal to 4 minus x squared? Okay, take a look at this. Add x squared to both sides. You have x squared plus y minus 2 quantity squared is equal to 4. Yeah, so right here, this is the standard form for a circle of radius 2 centered at 0, 2, right? Now it turns out, it just turns out to be really nice that if you just take the same equation and now solve for y, we'd be essentially reversing all our steps. We just have to be careful. Let's just show the work here. Yeah, let's solve for y. So we'll have, y minus 2 quantity squared is equal to 4 minus x squared. And then if we square root both sides, we'll have y minus 2 equals plus or minus root 4 minus x squared. Now the plus case we've actually just seen all the work for. What I'd like to do is pursue what happens when we look at the minus here. So let's just take the minus, and then we'll have y minus 2 is equal to negative root 4 minus x squared. The point being, if we now, let's just reorganize this by adding 2 to both sides, you have y is equal to 2 minus root 4 minus x squared. And this equation is actually the equality version of what's right there. So the point really being is, what does this projection look like in the xy plane? Well, it's really that entire equation, both the top part and bottom part. So let's just go to 0, 2. Yeah, so right there is supposed to be the center of a circle, and then radius 2, so we should go up to 4. It's actually this circle right there just filled in, right? And so this number down here is picking up the bottom half of that circle, while this number right there is picking up the top half of the circle. That's all that's really going on here, right? So let's now try to organize cleanly what is going on with this equation just by writing this in a slightly different format. This is going to require a little bit of work with some polar coordinates, but we can take this and let's write this out by foiling, and we'll have x squared plus y squared minus 4y plus 4 is equal to 4. Let's subtract 4 on both sides. Okay, and I just have to admit this question does involve a lot of work with polar coordinates. Okay, so maybe don't worry about this one all too much. But if we subtract 4 on both sides, we'll have x squared plus y squared minus 4y, well, is equal to 0, right? We've got to get rid of the 4 on both sides. The whole point now is it's actually going to be relatively nice to convert this into polar coordinates. So check this out. The first two terms, x squared plus y squared, that ought to become r squared, right? Minus 4 times, and then there's a y there. Well, let's turn that y into r times sine of theta. Okay, equals 0. Now, we do need a little bit of kind of odd trickery here, but let's add the negative term to both sides. Have r squared is equal to 4 times r sine theta, and then divide both sides by r. Okay, if we divide both sides by r, assuming r is not 0, kind of a usual calculus limit kind of argument here. Let's not worry about it too much here. But we'll have r is equal to 4 times sine of theta. And it is, in fact, this equation right here that describes the boundary of this filled-in circle. Okay, so in polar coordinates, it's the same circle that you travel around using r is equal to 4 sine theta. Okay, so here's the thing. We're only going to actually need this for theta going just between 0 and pi. I know that sounds a little strange instead of going from 0 to 2 pi, and it's really just simply because this entire circle is traversed. Notice the value of r is 0 when theta is 0 radians, and then if you plug in pi radians for theta, well, sine of pi is also 0. So right when you end up hitting pi radians for the angle, you end up going through the circle once all the way through. So what do we take from all this? Oh, there's also this right here. So let me just actually copy paste this down below. So those are the bounds for z, right? So we have this information here. It was telling us that z went between negative root 4 minus x squared minus y squared and positive root 4 minus x squared minus y squared. So let's convert that information into polar or cylindrical coordinates as well. So z should go between negative root 4 minus, well, the negative quantity x squared plus y squared again becomes r squared. You've seen this a lot already now. Let z less than or equal to root 4 minus r squared. Okay, so those are our z bounds now rewritten for cylindrical coordinates. And then we have actually from here that r should go between 0 at the smallest all the way up to 4 times sine theta at the largest. And then theta from up here should go between 0 and pi. Whew. All right, so that's a lot of pieces. Let me actually just copy the integral that we had here. Back in the question, you probably already written this down in your notes, but I'm just going to copy paste this down here. And now with there, we'll put that there. So where are we going to stare? We're going to look at this for the z-bounds, right? Because that's written in polar or cylindrical coordinates. We're going to look here. We're going to look there. And then we'll just have to convert all the pieces now. So we'll have an integral, something, something, something. Let's just space out the integral sign so we have some room to deal with this. Let me underline this in a color just so that we can see what's going on. So we've got x squared plus y squared quantity cubed. Well, that x squared plus y squared should turn into r squared, right? And then we'll just stick that in parentheses, quantity cubed. You could write already r to the 6th. I'm just not going to worry about it. What about, let's actually, sorry, I didn't notice this earlier. There was a cosine of z. What do we do with the cosine of z? We keep it because z is a cylindrical coordinate too, so we don't have to worry about it. There's no need to replace it. Now, the volume differential here, dz dy dx. So let's write that here. I've underlined in green. Well, there's going to be an extra r, right? That's the extra factor of r that popped out from polar coordinates. And then let's just go with, it turns out to be very useful to integrate with respect to z first. And then we'll do with respect to r and then with respect to theta. Now, all we need to do is put the bounds in place, right? So for the z, look at the red box earlier. So go integral from negative root 4 minus r squared all the way up to positive root 4 minus r squared. Then what's next? R is next? Yeah, from 0 to 4 sine theta. And then lastly, theta going from 0 to pi. Okay, if you're going to actually do the integral, it's actually not really bad to do the integral. We're not going to do it, but I would just, rewrite the r to the second quantity to the third times this extra r as r to the seventh, of course, right? You want to do all your algebra cleanups before you do any integration. Okay, just some reminders of some things. I don't think we've explicitly said it for cylindrical coordinates, but I think you've kind of noticed this kind of thing already with some of the other integrations that we've done. This over here, we'll just say that this, the inner integral, at least in our setup here, is with respect to z, so it can mention the outer variables. So you can mention r and or theta. We've only mentioned r there. Now the next integral, you would have been done with the z, and you've already plugged in something for z using the fundamental theorem of calculus. So then this next integral, the bounds can only mention the outer variable theta. So you can mention theta. You don't have to. We did for the upper bound. And then finally, as to be expected for the outermost integral, this can only mention constants. Can only be constants. Okay, and then I do have, real quick, an interactive question, and it will look like this. How about, let's write this down here. Okay, so, interactive question. Let me just, all right, so when... this is not related to the last question necessarily, so just in general, when working in cylindrical coordinates, just working in cylindrical coordinates in general, let's just write it out. In cylindrical coordinates, what happens to the value of r as z grows? So there's the question itself. I hope I'm making sense with what's being said here. So let's just put this a little bit, sorry to be a little informal, but a little bit in the language of the previous chapter. So tell me about the partial derivative of r with respect to z. What's going on there?